do the normal thing where I make some announcements about the course, a couple things that are upcoming, a couple of web work assignments due later in the week. So make sure you're working on those, that you have a, excuse me, make sure that you've completed those as best you can. I think that I noticed that someone pointed this out actually, but there was a discrepancy between the due dates that you see on Canvas and the ones you see on WebWork, but I think now they're in alignment. So I forget the number, but I think like WebWork 8 is due this afternoon and WebWork 9 is due on Friday. So everything's, I think, in alignment right now. So you might want to check that. But those are the ones that are due this week. Primarily, they concern stuff that we talked about last week, where we are worried about things like basis and dimension. I mean, that's largely what they concern: subspaces, basis, and dimension. Next week, probably we'll have some discussion of vector projections, which is mainly the content of this week. So we're actually a little bit ahead. With that in mind, I'd like to spend some time today talking a little bit about written assignment 2, a few of the problems. I started grading those and I noticed, noticed a couple things that I feel like I need to address. So I'll talk a little about written assignment 2, a little bit about the problems there. I guess you can stop me whenever you think it's appropriate to do so. I won't do all of the problems, but at least some of them. And I think later I'll probably give some summary of where we want to go with what we talked about yesterday and what the main important points were. So let me share the screen. So this was written assignment 2. I've gone through several of them already. I want to be able to, to talk a little bit about some of the problems, how you might, write about some of these problems, how you might think about them. In particular, I think I want to talk about problem 1 a little bit, maybe problem 3 a little bit, in particular parts 3 and 4, maybe a little bit about problem 4, and then 5 and 6, we'll wind up referring to later time. So on problem 1, you have these 3 vectors. You've got 1, 3, 3, 2, 3, 6, and 1, 4, 3. It's 1. Let's see, remember what that is. 1, 1, 3, 2, 3, 6, and what is that? 1, 4, 3. So when I was looking at this, when people were completing this problem on the ones that I've graded, I think people understand procedurally how to approach this problem. So the question is, are the vectors linearly independent? So the way that most people are trying to address this problem, and I'm not saying it's wrong, is that they begin to row reduce the matrix and they hope to get something out of that. So I'm going to go a little bit further on that when I provide this answer. So to see this, we're looking for non-trivial dependence relation among the columns of this matrix. Let's call it A. And the reason is that, well, that's the definition of linear. If we can only find the trivial relation, that's the very definition of linear independence. So I guess we look for those relations in the null space of the matrix A. So the null space of the matrix will contain all non-trivial relations among the columns because of what the null space actually is. And so it's not only the case, so I think on this problem, I think it's not only the case, what most people are saying is that they row reduce this thing and they notice that that last row is a 0 row. That's not surprising, because if you look at the last row of the matrix, it's pretty clearly a scalar multiple of the first row of the matrix. So when you begin to row reduce and put this matrix A into reduced row echelon form, you immediately see that that you have an issue. Well, it's not really an issue, but you immediately see that there is you immediately see that the matrices of rank 2, which I guess makes you think that they're linearly dependent, and that's what most people are writing. I think in the solution I'm about to give you here in the discussion, I think I'll probably want to exhibit a dependence relation so you can actually see how you might write one of the columns in terms of the other two. So if you have this matrix A here, and you row reduce it, you start with the first non-zero pivot, you kill the terms below that pivot, and so on. What you wind up doing when you perform the elementary row operations, this matrix is convertible well, okay, so I won't give the exact answer. So, in discussion, this matrix is convertible into something that looks like 1, 2, 1. You have zeros here. I want to think about, in fact, the augmented matrix. Well, let me just rewrite things a little bit. I want to think about the augmented matrix that is associated to this matrix. So it would look like 1, 1, 3, 2, 3, 6, 1, 4, 3, and then column of zeros. So if that's the augmented matrix, if that's the matrix that you're using in order to try to understand, whether or not there's anything in the null space to discuss, how does it actually row reduce? So this augmented matrix is convertible into 1, 2, 1, 0. You're going to have some zeros here. You have -1, then add, conveniently enough, that's also a 1. I guess that's a 3 right there. That's still a 0. If you multiply the first row by -3 and add it to the last row, you can pretty quickly see that you get a row of zeros. So that's this guy right here. So I won't write down the row operations, but you know what they are, I'm sure. So in the first column, you have 1, 0, 0. In the second column, I use the second pivot to eliminate the 2 above by multiplying the second row by -2 and adding it to the first row. So I get a 0 there. -2 times 3 is -6. So you get a -5 there. So I have a 3, you have 2 zeros. Now, if you're at this point, we can observe that the 0 row, or the fact that you've got two columns with non-zero pivots and one without any, we can observe that there are some free variables. There's one free variable. And so the null space of A contains a non-zero element, at least one non-trivial element. What I would like for people to think about, or when they're thinking about developing a solution for that problem, what I would like for them to consider is that anything in the null space of A is actually going to be giving you a non-trivial relationship between the columns of the matrix. So to actually write down what one relation might be, just take one of the basis elements, take a basis element that you found for the null space. That basis element is going to encode a relationship between the columns of A. So if you want to take this problem and go a bit further, just check to see that, your basis, and will be unique in this case because the null space definitely has dimension 1. Your basis element, there's one of them, gives you a relationship between the 3 columns. So it actually allows you to say what column 3 is in terms of the first two columns. So, the main point of the exercise, I mean, again, you're just trying to see if you have some sort of non-trivial relationship with columns. You definitely do. But I want people to know, when you're thinking about that problem, the reason why you can be sure of that is because the null space has contained within it all possible, in some sense, the weights for all linear combinations of the columns. If you can find a non-zero element in the null space, then you have a non-trivial relationship among the columns. Yes, there's a question.
Should we have like equal, instead of like equaling the vector to the zero vector, should we have equaled it to like let's say v1, v2, v3, so then we can look at the relationship that way?
I don't think that's necessary, because if you're thinking about what you're just describing, you're actually trying to find any restrictions for the column space. So when you talk about setting, if you talk about setting up an equation ax equal to v or something like this, the question you're trying to address with that are, what are the possible v's that you can solve for? So when you're thinking about linear combination, when you're thinking about whether or not the columns are linearly dependent or not, the actual question, the way you resolve that question is by studying the null space of the matrix. And that's because the null space of the matrix will contain all possible linear combinations of the columns that exist. So, and so how many, or at least the ones that add to zero, right? Because if you solve, you're trying to solve ax equal to zero when you're discussing the null space. So if you can find an element in the null space, which is not the zero vector, what that means is that the columns of the matrix, the matrix that you're talking about, are linearly dependent. So in this particular example, since the matrix is such that it's got two columns, so the reduced row form of the matrix is such that it's got two columns which contain non-zero pivots and a third column which does not. What that means is that if you're actually trying to find a formula for the null space in terms of vectors, that formula will involve one free variable and therefore one non-zero basis vector. And if you just stare at that basis vector for a minute, you'll realize very quickly that the basis vector that you get is giving you a relationship among the columns that you can use to solve for the third column in terms of the first two. But with what you're talking about, if you're thinking about like, well, okay, look, I'll put a vector on the right and kind of see what I get. What you're really trying to address there is what kind of vectors can exist as linear combinations of the columns. So, and the reason for this is because matrix multiplication, if you take A times B, the product of a matrix A times a matrix B will be some matrix, but the columns of the product matrix are linear combinations of the columns of the first factor, the A, with weights given by the columns of the second factor. You only have one column in the second factor in this case, so the product A times X is just a linear combination of the columns, and the linear combination that you will get will vary depending on what you choose for the values for the components of X, I guess I would say. So questions about dependence are usually questions about dependence of the columns, typically addressed by thinking about the null space.
Okay.
Because the null, I mean, the thing to remember is that if you think about it a bit, you'll realize that the null space must contain all possible combinations, linear combinations of the columns, which add to zero, simply because of what the null space is. So I'm not saying that people's answers to this question were like wrong or somehow deeply disturbing or anything like that. But I would like people to think a little bit about why they're answering the question the way they are. So if you have the matrix, you row reduce it, you get a zero row. And because of that fact, you know that the columns are linearly dependent. I mean, that's true, but think about why. You can give, yeah, I mean, just go into some detail here. It's useful just to keep things straight. Just think about why that is. It's not an incorrect fact. It's an actual fact, not a fake fact. But it's one that's worth dwelling on, thinking about why that's true. So I guess in the end, thinking a little bit at least about why some of the stuff we're saying is true, it's probably important. But so far, when I'm in the homework that I've been grading and the written assignments I've been grading, people are getting that question procedurally correct pretty much every time. But there's more to it, I guess. So think about the part that's more significant than just the row reduction. The fact that you do get a 0 row is important, tells you that the matrix is of rank 2. Essentially this is saying that the dimension of the column space is 2. So 2 of the column vectors will suffice. We already know which ones they are, but it's the third one is out. So anyway, I mean, just think through why, I guess.
So although like the vectors do span the vector space, it's not a basis in R3 because they're not linearly independent.
Yeah, so they're not linearly independent, and it doesn't even span R3.
Oh, it is.
So if you think about it for a minute, R3 has dimension. This is another good question. R3 has dimension 3.
Oh, so it needs
right?
3 vectors.
Yeah, and so you actually need three. You need 3 linearly independent vectors in R3 in order to span it, right? But if you look at the set of vectors, you actually have 3 vectors in this set, but one of them is redundant. You can actually get a formula for the third vector in terms of the first 2 by taking essentially any element from the null space of A. Any element from the null space is actually going to give you a dependence relation that you can use to solve, well, I mean, except for the 0 relation, which is unimportant. So I guess I should say any non-zero element of the null space is going to give you a dependence relation, which will allow you to solve for the third column vector in terms of the first 2. So you don't even get all of R3. You get some subspace of R3, which is like sort of slicing through R3, like a plane. You get something that's of dimension 2. So if you're talking about the dimension of the spanning set, if that set of vectors is an S, and you're thinking about the dimension of what that set of vectors spans, it can't be all of R3 because it only has 2 vectors within it, but R3 needs the third vector. If you wanted to get rid of that third vector and you ask yourself, look, how do I extend those 2 vectors to a basis for R3? It's a pretty interesting question. And it's a lot more related to your first question about putting the V in there. If you take those 2 vectors and have that be, and you think about, well, what kind of things are in the column space? This is also a question about solving. This can also be cast in the form of some equation. But you're going to wind up getting a restriction on what can even be in the column space, right? It's going to be some 2-dimensional restriction. So in order to get a vector which would complete the set of 2 vectors to a basis, all you have to do is select the vector in R3 which does not satisfy the particular condition that's imposed when you sort of put all those guys in a matrix. Again, that's an interesting question. How do you actually complete a set of 2 vectors to a basis? It's good to know how to do that. Basically what you do is you try to figure out what the column space of those 2 vectors is beyond, talking about the fact that it's spanned by the first 2 vectors. You want to think about the sort of restrictions that must be true for any vector in R3 to be within the column space. And once you kind of write down what that restriction actually is in a sensible way, any vector that does not, you can always manufacture a vector that does not satisfy the condition that would come about by solving some equation like that. And so if you pick anything outside the restriction, you're going to get a third vector, if that makes sense. So I guess all I'm saying is if you're trying to complete it to a basis, think about the column space, which of the 2 vectors. So this entails thinking about, we know that the first 2 vectors span it. I always have to remember what they are. So it's 1, 1, 3 and 2, 3, 6. So, when you reduce 1, 1, 3 and 2, 3, 6, that set of 2 vectors spans the same subspace of R3 as the original set. It isn't a basis for R3 because it doesn't contain enough vectors. How can we be sure of that? What does column space, when you put those things in, what does the range of A look like when A is equal to 1, 1, 3, 2, 3, 6, right? This is a question about but an equation that looks like this, like what kind of V are reasonable? So the thing is, you're dealing with a 3x2 matrix. And so, when you form an augmented matrix in this case, if you really want to solve the problem, and I'm saying it's interesting, you might want to try, the augmented matrix would look like that. But if you proceed to row reduce, after some steps, if the matrix is totally row reduced in the first 2 rows, after some row reduction, you're going to get 1, 0, 0, 1. You'll have some guys over here, which are the combinations of the V's, and you'll also have 0, 0, and some third guy. That third guy will also be a combination of the V's, but for the system of equations to be consistent, that last guy has to be equal to 0, and that's the condition that you want. So once you identify what that condition actually is, if you pick a vector in R3 that doesn't satisfy that condition, then that vector cannot be in the column space of the matrix A. And so you would add, and there are lots of choices, you would add that third guy into the set, and you would have on your hands a basis for R3. So in a sense, trying to extend, if you happen to have a linearly independent spanning set for some Rn, it's possible to, one element at a time, extend it to a basis for Rn just by basically solving for some equations. Solving some equations, or thinking about like when equations can be solved, I guess I would say. And the conditions that you would see as part of the process will gradually allow you to build up to a basis for the entire vector space, if that makes sense. Is that all right? I mean, it's an interesting question. It's worth thinking about. I think in a lot of the web work, and I think in a lot of the work we're doing so far, we've gotten pretty good at throwing out vectors. So if you take a look at those 3 vectors, because the row reduced form looks a certain way, it's pretty clear that the third vector is the one that's redundant, so you can discard it. We're good at moving down to a basis. Of course, moving up from a spanning set to a basis, it still involves solving some equations, but you have to think through how you might do it. So it's another question worth thinking about. Might put that on some written assignment at some time, maybe this week, just so people get a chance to think about it a bit. Other sort of general comments. I don't really want to talk about 2 that much. Again, I think people have a pretty good understanding of how to at least formally compute a null space. I'd like to make some general comments about this matrix. If you look at it, I guess it's 3x5. The maximum rank for this matrix, the maximum number of columns that have non-zero pivots, I guess, is 3. So in this particular problem, you're sort of expecting that any basis for the null space will contain at least 2 elements, maybe more, depending on how the matrix reduces, I guess. On 2, people were answering a question that I didn't ask, but it's okay, the answers that they gave, at least so far. So on 2, the column space of A is defined as the subspace of R3, which is spanned by the columns of A. Question is simply, do the columns of A form a basis for the column space? Well, by definition, the columns of A span the column space of A. There's no question about that. But if you're thinking about whether or not the columns form a basis, you're actually trying to ask the question, are the columns, well, we already know that they span, are the columns linearly independent or not? And so all that's really required on that problem is just to address that. Do you think that the columns of A, if you kind of put them all out there, do you think that you have a linearly independent set? Now, what I would point out about this is you have an awful lot of vectors there. If you row reduce the matrix and then try to figure out what's in the null space, like in part 1, I forget exactly how many free variables there are. I think there may be 3 actually. There are 2 or 3. I think it's 3 if I remember the solution right. But in any case, what that means is that the null space contains many non-trivial relationships among the columns of the original matrix. And so any one of those, pick any one of them out, right? And you're going to be able to figure out that the columns are not linearly independent. you're always going to be able to write some of the columns as functions of the other columns. And that's basically what the elements of the null space will reveal. If you stare at the null space that you have long enough, you realize that the numbers that you see are actually coefficients in some linear combination of the columns. And so when you write down the linear combination of the columns associated to the basis elements in the null space, you're going to see exactly what the relations are between all of the columns. So, you're going to be able to discard columns. And I think in this problem, what most people are doing is they say, look, I row reduce the matrix. I notice there are a couple of columns where I have non-zero pivots. I just pick out those columns in the original matrix, and those are going to be the elements in the basis. So the answer is that, what you have is not a basis because you can always reduce it. But again, I'd like people to try, to go back and think about it a bit, try to address the question as it's written. You don't really have to exhibit a basis in order to understand that that thing's not a basis. But the point is to realize that the null space contains non-trivial relationships, weights that determine linear combinations of the columns that add to zero. That's actually what's in the null space. And so if you have in the null space a vector that is not zero, you pretty much immediately know that the columns are not linearly independent because that particular element in the null space is giving you the non-trivial relationship between the columns. If you're really careful about how you row reduce the matrix, then you're going to be able to write down the redundant columns in terms of the columns that you want to pick out as the basis. And that's because the basis for the null space that you should get is essentially going to give you the formulas for those relationships, if that makes sense. So I'm not saying that people, like with the written assignment, I'm not saying that people don't have a procedural understanding of how to find a basis. It's just think it through. You row reduce the matrix, you can pick out the columns in AA which form the basis, but why do you really believe that? Why do you think that what you're writing down is true? Go back and think about the elements of the null space, consider them, and then think about why they're giving you relationships among the columns of A, which essentially show that a lot of the columns of A are redundant, that they can be written as linear combinations of some essential set of columns within that larger set of columns. The essential set of columns, you'd normally call that a basis. So again, go back, dwell on it a bit. Again, I'm not that, procedurally, yeah, people get it, but just be careful about it. Talking a little about part 3 and 4, I'd like to basically use maybe this example of a row reduced matrix as a motivation for discussing this. So what I'm hoping people will do, what I was hoping that people would do on 3 and 4 is give at least some argument in context about why in a reduced row form or in an 8x10 matrix that's reduced row echelon, why these things are true. So I guess I'll just write down some generic matrix which looks like this. Maybe it won't be 8x10. Maybe that's going to get too tedious to watch, but maybe I'll write down like a 4x5 or 3x5 or something like this. So a matrix that's in reduced row echelon form might look, so I guess that's it's 3 columns, right? So the matrix that you see before you is in reduced row echelon form. Now, who knows where it came from? Maybe it came about as part of some row reduction for some problem you're trying to solve. It doesn't really matter where it comes from because the matrices that you're thinking about in parts 3 and 4 are already in reduced row echelon form. Now, when you think about part 3, you're trying to show that the rows are, you can pick different numbers, or you can put asterisks in there if you want. Doesn't really matter, but you want to be able to show the rows are the non-zero rows are linearly independent of a matrix that looks like this. Now, when we're thinking about this, we somewhat confusingly if we're thinking about vector spaces the way, if we're thinking about Rn the way that we normally think about it, we typically think about the transposes of the rows. But if you look at those vectors, you get 1, 3, 0, 0. It comes from row 1. You get 0, 0, 1, 2, 0. That comes from row 2. From row 3, maybe you get that, right? So the matrix that I wrote down, I guess, is of rank 3. It's about as big as it can be in this case. Why would these rows be linearly independent? Let's write down a dependence relation. So any dependence relation among those vectors looks a bit like this. So it looks like C1, 1, 3, 0, 0, 0, plus C2, 0, 0, 1, 2, 0, plus C3, 0, 0, 0, 0, 1. And if it's a dependence relation, then that needs to add to 0. So that's just a generic dependence relation. So does everyone see, if you're trying to figure out whether or not a set of vectors like this is linearly independent or not, you are studying dependence relations that look like this. If it turns out that the values of C are all equal to 0, and that's the only dependence relation that exists, then the vectors that you're talking about are linearly independent. There aren't any redundant vectors. But if you can find a non-trivial dependence relation, if you can find some values of C which are not all 0, so that the left-hand side adds to 0, well, in that case, then you're thinking about that there's a dependence between those vectors. The vectors are linearly dependent in that case. They're redundant vectors. So in this case, look carefully at the form of the vectors on the left. If you look at them, they come from the row vectors, but notice the form they take on. If you look at C1, C2, and C3, the vectors on the left-hand side have to add to something like C1, right? And then you have some zeros up there. And then you have 3C1, right? Because you have zeros there. Then you've got C2 and then 0C3. You've got a 0, a 2C2 below that, I guess. And in the final entry, you have C3, and that has to be equal to the 0 vector. Now, the reason why you're getting a pattern of coefficients that looks like this has everything to do with the fact that the matrix is in reduced row echelon form. When you stare at the form of the matrix, if it's in reduced row echelon form, you immediately know that C1 is equal to 0, I think, from this. And in fact, you know they're all equal to, in fact, you know that all the coefficients are equal to 0 in this example because of the structure of the reduced row echelon form of the matrix. So if you stare at this for a minute, you know that that left-hand side has got to be equal to the right-hand side. And how can that happen? That C1 is equal to 0, that C2 must also be equal to 0, and C3 must also be equal to 0. So what that's saying is if there is a dependence relation, there's only one dependence relation that it could be. It's the trivial one, with the C1 and the C2 and the C3 is 0. Now, what I'm trying to say is that the generic 8x10 case, where you don't really know what the numbers are, is the same. And it's the same essentially because when you think about taking the non-zero rows and you look at the transpose of the various rows as column vectors, when you write down a dependence relation, what you get is predictable, right? Like the C1 will always have to be 0 in a case like this if the matrix is in reduced row echelon form. And then in the second place, maybe there's a combination of C1 with C2, but maybe it's got to add to 0, so you get a C2 equal to 0 and so forth. So it's better on these problems when you're thinking about trying to show that some matrix has linearly independent rows, like in this form. It's better just to sort of realize this observation, in general with some sort of set of equations. And when you sit down and look at that set of equations, you realize that, in cases like this, the only thing you have is the only linear combination of the non-zero rows thought of in this way is the one that's trivial. And problem 4 is very similar. It's in some sense maybe even more direct, because if a matrix is in reduced row echelon form and all you care about are the columns with the non-zero pivots, what kind of columns are you talking about? The columns with non-zero pivots, you're ignoring that column. I guess it's the second and the fourth column. Which columns have non-zero pivots? 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so if you're only looking at vectors that look like that, that's actually the standard basis. And you can easily show, that's the standard basis for R3, and you can easily show the standard basis is, consists of vectors which are linearly independent. It's easy to see. Sometimes you might not get all of them, depending on whether or not you have any 0 rows around. This is just one example. But what you wind up with is a 1 somewhere and zeros everywhere else. And if you write down these columns that have non-zero pivots in order, what you're going to see is that the 1 is occurring in different places along these columns. And so when you write down a dependence relation, the only dependence relation that could possibly be, the only dependence relation that really makes any sense is the trivial one, because of where the 1s and the 0s are in those types of columns. So I'd like people maybe to go back and think about that. It could be that people didn't quite realize what I was after on those problems. I made some comments on the homework I graded, but worthwhile going back, thinking about it a bit. When you're thinking about an 8x10 matrix, just write down some generic example, what that might look like, depending on, there are a lot of them, I guess. Just pick one, choose a particular rank and then go with that. I don't really care, whether or not you want the thing to have rank 8 or rank 3. It doesn't really matter for the argument that you're trying to give. So does this make sense so far? Go back and think about it, right? Think it through. Again, it's true. And I think most people, because of their answers when they're looking at matrices where you're actually having to do some computation, totally believe it. But, think through why it's true. Look at the form of a reduced row echelon matrix. Pause for a moment to think about why a statement like the non-zero rows of a matrix in reduced row echelon form are linearly independent as a set of vectors. Think about why it is. It's the structure. It's the structure of the matrix, which is basically giving the result. The ability to solve, the ability to solve a system of equations uniquely for the 0 vector. That's really what we're talking about here. So, pause for a moment, think a little bit about it. Overall, but again, that might take time, but it's worth going back considering. A little bit about 4. People, I think, kind of got the idea of it. Just be careful about what you write. I don't really want to write down any examples, but on 4, what I was after is just some set of examples. So you don't really have to invoke on 4 any sort of general principles, which, might be, or you don't really have to invoke anything which might be thought of as a set of general principles, I guess. But I guess you could. But what I have, and maybe you should on your own, because if you have an example, you probably have a pretty good idea of what general principles are at work. But examples are good. And basically these are kind of 4 cases which, although you can sort of write down examples in 1 through 4, which are pretty elementary, I think. Just think about it. They sort of characterize lots of different things, almost everything that could actually happen that we might have an interest in when we're dealing with matrices as functions. So go back again, think about it a bit. If you turned it in, recently, I might have graded it. I might have made some comments about 4, given some suggestions. If I had some objection to what you wrote, I probably would have noted it in the comments. But in any case, I'll probably have some more comments, I guess, next week after I finish grading written assignment 2. But overall, I guess what I would say on the basis of the assignment is procedurally, I think people are on pretty sound footing, but go a little bit further if you can. Think a little bit more about why things are true. In particular, think about linear dependence and independence. That concept winds up being pretty important. So do people have questions about this so far? That's really all I wanted to say today about the written assignment 2. I may return to some of the problems next week. So any questions that people might have about it? Is this okay?
Yeah, it's okay.
Well, I'd like to spend some time talking about where we're at right now and where we might be going. Today we're going to talk about, so I'm not sure if I put the notes up yet on Canvas, but I will, but I think I probably will after class. So yesterday we talked about something called least squares. So in most linear algebra books, this topic is at least addressed, but to be honest, I think it's probably in most linear algebra books because they have to make it appear that the book has some practical application to what people might actually be doing at some point. In particular, least squares approximation has a great deal to do with statistics. A lot of what you do in statistics is sort of regression, but it's some hidden form. You're talking about there are a lot of linear models in that course, and least squares approximation or finding the line of best fit, if you've taken such a class, is one of those things. That's why it's in there. So in most books, this is something that that's in there. You can see the formulas. They're in this chapter 3 of the text. They're in the notes as well. To be honest with you, actually going down and solving a problem using least squares approximation by hand is something that you will never do personally, and that's for obvious reasons. If you're thinking about the least squares problem, you usually have a data set consisting of hundreds of different relationships, and you're not going to write down some large inconsistent system of equations and figure out what the transpose of the matrix is and what the product is by hand. The reason why you tend to see things like normal equations presented in books is not because you will ever actually use these equations to compute anything. A computer will do that. One reason is I think authors of such books want to give an idea about what the underlying mechanics are behind what the computer is doing. So you have some idea of what's going on. I don't really want to give you the impression that you're going to be doing any of that by hand. And in fact, even things where you're trying to project a vector down onto some subspace, you're not going to be doing by hand. But the things like the normal equations and seeing them is important, I think, conceptually, and I'll try to describe why that is, and then we'll talk a little bit about the idea of a basis, of a particular type of basis, which is thought to be useful. But I hope that the initial discussion might provide some motivation as to why anyone would want to talk about some of that at all. So, remember last time we talked about least squares, but really, you won't be computing by hand. So that's not really the importance of it, though it might appear otherwise. If you look at most books, wind up computing some least squares approximation by hand, but that's not really why it's there. So the discussion I want to have today is, so the important part, at least for me, I guess personally, it's this question. We know how to project a vector B in Rm onto a subspace of Rm spanned by some vectors A1, A2, A3, let's say n of them. For the sake of the question being an interesting one, you typically have to pick n being less than m. And again, for the sake of simplicity, you usually assume that those vectors are going to be linearly independent rather than dependent. Otherwise, you'd throw a few out. Really just think about a small linearly independent spanning set for a subspace. So we already know how to do this, and it's done through the so-called normal equations. And normal equations, it's basically saying something like this: denote the projection of B with the symbol P. Normal equations are, it really just looks like one equation. It's called equations because there's usually more than one component in the vector. But the normal equation, I guess for us, looks a bit like this. It looks like A times A transpose A inverse A transpose B. And so remembering, that A transpose is A with rows and columns swapped. Now, actually one more thing. When you're talking about the projection, I guess one more thing I should say here, remember that there are all sorts of ways to sort of put B into the subspace of Rm spanned by those vectors, but we're looking for the one that minimizes some distance. So the projection P minimizes something that looks like this. So I'll call it, maybe confusingly, x minus b squared. Now, in courses like statistics, you generally talk about least squares approximation, and that's the meaning of it. So you're minimizing some squared error term. And so the vector P, the projection vector that we're talking about into the subspace, what we're saying is that the size, the gap between the projection vector and the vector B is the smallest that it can possibly be among all possible vectors that B could go to within the space spanned by those n vectors A. So, there's this big lead up. You talk about some geometric intuition associated with the problem. You talk about calculus. It looks all complicated, and at some point you just have to ask yourself this question. Why is this formula so complicated? Why? And so it's not, or maybe better, what features of the problem, what features complicate the calculation? Anytime you see anything weird in a math course, you should always wonder, why does it look that weird? Now, often, when you're writing down a bunch of stuff, when you see the derivation, you're supposed to be totally convinced that this process will do it. But the truth is, most people probably aren't. And a natural question is, why isn't it easier on that than when why isn't it easier than what I'm showing you? Why doesn't it look like something else? So one thing that I would point out is, if I took anyone in the class, or if anyone in the class was just put on a desert island for a while, and you ask them this question, look, I have a vector P that is not in the span of a collection of n vectors within Rm. And my goal is to understand how to project P down onto the subspace spanned by those vectors. Now, people would come up with a first solution to this. Now, for most people, that solution would be wrong, but it's wrong in a really interesting way. In fact, it's productively wrong. And so here's what I think most people would do if left to their own devices on the desert island with nothing to think about but linear algebra for like 3-4 hours a day. So we can conceptualize the vectors A1, A2, and so on as coordinate axes which define, the span, I guess, which define the subspace of Rm which they span. For example, in R4, we might have the vectors 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, And maybe that's my vectors A. So, you know, those vectors A are much more naturally a set of coordinate axes because, you know, if you think about things in 4 coordinates, most people think of W, X, Y, Z, or X, Y, Z and something else, or X, Y, Z and T or whatever. In this case, maybe that guy represents the X-axis, that guy represents the Y-axis, that guy represents the Z-axis. If you're in R4, there's some other axis that isn't named. So if you're thinking about the nature of the subspace that is spanned by those 3 vectors within R4, you're basically just looking at a copy of 3 space, and there's some other guy out there, some other axis. Can't really draw that; it's 4-dimensional, but that's maybe sort of the setup for the problem. You actually think of them. You actually think of an element of R4 written in terms of those coordinate axes, if that makes sense. So if you have a vector like 3, 4, 3, its coordinates are 3, 4, 3 relative to those vectors. So are you with me so far? So when you write down 1, 0, 0, 0, 0, 1, when you write down those 3 guys right there, what most people are really thinking of are the X, the Y, and the Z axis embedded within some larger space, R4, where there's some other axis, call it T if you want to. That's not, it's not named. Now, if you have a set of vectors like A1, A2, A3, and so on, it's a bit like that. For example, in R3, or in R4, you know, we might, on the other hand, have, you know, a set of 3 vectors that looks like this. And those 3 vectors, it turns out, span the same subspace as the of R4 as the vectors that I wrote down initially. And they can also be used to form a system for coordinates. So if you have a vector in R4, you can write any vector, at least any vector within the subspace spanned by those 3 vectors as a linear combination of the vectors that you see. And you know, the coefficients associated to the vectors are the so-called coordinates, I guess, the coordinates of the vector. For example, if you think about it for a minute, it's pretty clear that you can write stuff down, like you can write down 2, 3, 4, 0, you know, as a linear combination of those vectors. I mean, first of all, you know, the last guy has to be 4. If it's 4, then I guess you have to have a -1, 1, 1, 0, 0 here. Given that you have 4, -1, I guess that would have to be a 2. So, you know, this may be wrong, but it's close enough. So if you have something like this, it seems like 2, 3, 4 is this linear combination, and the coordinates of the vector 2, 3, 4 are 2, -1, and 4. So when we project along axes or coordinate axes within the subspace that are defined by this set of vectors, we would say that 2, 3, 4, 0 goes to the 3 vector 2, -1, and 4 when we project. So the numbers that you see in front of those vectors have something to do with where the vector wants to go. Does this make sense so far? Bear in mind, no one would do what I just did. If you're thinking about a subspace of R4 or any subspace of Rn, the vector space that people would most naturally choose, or the basis that people would most naturally choose when thinking about such a thing, would be one that looks like this, rather than one that looks like this. That's just too weird. You know, it's not natural to think about coordinate axes defined by vectors which are somehow skew. For people that have been doing mathematics for many years, it's much more natural to think about subspaces spanned by, or in some sense defined by, coordinate axes which are perpendicular, and that's because you've seen that your whole lives. That's what makes the most sense. So that's in a sense the reason why least squares formula looks so complicated. So no one would pick the second way. If you're left on a desert isle, when you think about a spanning set for some subspace of Rn, it's definitely the first example that you would think of if you're just left alone, not the second one. Now, you'd probably also think of this. It'd be wrong, but it's not crazy. It's right. It's right in a deeper sense, because it's how you should be thinking. We already know how to project a vector B onto a one-dimensional subspace. And that's because the trigonometry of the situation basically forces a certain formula. So I'll write the projection. So vector is within R4, or I guess I should say Rm. The vector AI for each I spans a one-dimensional subspace, spans a line. And so I'll call the projection P sub I just because I'm specializing it. The projection of B onto that one-dimensional subspace looks a bit like this. It's A sub I transpose times B divided by, in some sense, the square of the magnitude of A sub I times, is a scalar, times A sub I. So this guy's some number. So the numerator and denominator are dot products. That's one of the early formulas we got, I think, yesterday. So when people are thinking about just one-dimensional subspaces, if you're trying to build up a theory of how to project onto a subspace of Rm, which is spanned by all sorts of different vectors, it might make sense to start with just a one-dimensional subspace, look at that, and then imagine that the multidimensional problem is associated to these individual projections in the obvious way. So when you're dealing with linear spaces, the obvious way is just this. If the span of my set S, if S contains those vectors, is all linear combinations of the AI, why doesn't the projection of B onto span S have anything obvious to do with the individual projections, with the projections on, the most obvious relationship, the most obvious thing that could happen is that the total projection, so, or rather, why isn't the projection we want just the sum of the individual projections, like it would be if the axes were perpendicular? So if you're talking about projecting onto a set of perpendicular axes, I'll write down what I mean by this in just a second. But why isn't the total projection just equal to P1 plus P2, plus P? So I have n vectors. For example, it's definitely that way. So in R3, let's do it in R4. If I think about a subspace of R4 spanned by these three vectors, so it's S. Maybe I take a vector B, which is not in the span of those vectors, but it's pretty easy to see what kind of vector like that would look like. So let B be like 2, 1, 3, 2. You know that guy's not in S and not in the span of S because of the 2 right there. It turns out that the projection of B is what you think it is. It's 2, 1, 3, 0. You just project straight down onto the subspace, onto a subspace where you're dealing with the 2, 1, 3. You're projecting down onto the individual coordinates. So when you're dealing with this easy basis, the projection is extremely easy to define. And so, you can check that that's the same as the projection onto the individual coordinates, which maybe I'll do very quickly. P sub 1, if you're projecting onto the subspace spanned by 1, 0, 0, 0, all you really have to do is to take the dot product of 1, 0, 0, 0 with the vector and divide it by the magnitude of this vector right here. So the numerator, I guess, so if you're talking about the way we've defined it, we take 1, 0, 0, 0, 2, 1, 3, 0, and we divide by 1, 0, 0, 0, 1, 0, 0, 0, and we multiply that by the vector 1, 0, 0, 0. The dot product in the numerator is a 2. The dot product in the denominator is a 1. So the projection onto the first vector is just twice 1, 0, 0, 0, or even better, 2, 0, 0, 0. And in fact, that's true for the individual projections. If you project onto the second and third vector, you get a similar formula. And when you add up those individual projections, in fact, you get the projection of B onto P that's predicted by the normal equations. So when most people think about vector, yeah, go ahead.
So that equation, projection, like P sub 1 or I, I'm not sure.
P sub 1, yeah.
P sub I. What is that equation specifically for? I think you explained it.
Yeah. So the idea. So I'll draw this in. So something like P. So something. It's a bit like this. It's a bit like this. I can't really draw the exact situation I'm trying to describe, but I can draw a version of it. You have to imagine that. Let's say that that's a vector in, and that's another vector. So call this vector right here, call that B. So we're imagining vectors as arrows which are in some larger space. So I'm not really drawing the ambient space or any coordinate axes because that would just mess up the picture. So let's say that's B. And let's say that this vector right now, this guy right here, let's say that that guy is A. The projection of B onto A is the shadow of B onto A. So it's this vector. It goes in the same direction as A, but it's as though you take the end point of B and you draw a vertical line straight down to A in such a way so that line intersects A at a right angle. The vector that you get by connecting that guy, that point right there, to the end of where that second line crosses. It's too many things going on, but it's all right. A this way. This vector right here is what we're calling P. It's the projection of B onto A. Projection of B onto A is defined as the vector within A that you choose to minimize the distance. Well, it minimizes a certain equation, so I'll write it down. But that equation basically is, I'll say it in the picture. P is chosen in such a way so that it minimizes that distance right there, and that happens when that vector right there is perpendicular with A. So that's sort of the machinery that's going on in the background. Does that make sense?
You say that it minimizes the distance, like from going, I guess, from B down to A.
Yes.
But what, isn't like going vertically down like the most minimized distance?
Yes, that's the point. Exactly. Exactly. That's right. It is like any other vector which would connect A with B is bigger than the vector than just the vertical distance between the two, if that makes sense. You're absolutely right. And visually, the projection P within, so the projection is just a scalar multiple of A, which is chosen to minimize that distance. You could pick other vectors which are scalar multiples of A, but none of those vectors would minimize that vertical drop, if that makes sense.
Okay, and the projection, so but the projection is still, like you said, the shadow of B.
Yep.
Okay.
It's like the sun is above the vector and it's going right down. Yeah. It's above it, right? Not another weird position, but directly above it.
Okay, so then that's why, like, when you had the other slide with you named B 2, 1, 3, 2, and then P was just the same vector with 0 at the.
That's right. And so with the other slide, that's right. So with the other slide, I guess you're talking about that one. So the formula, so you have the picture, but the formula for projection looks a bit like this. So if you're thinking about the role of A is played by the same image, the role of P is played by the same image in the same image. But if you take a look at what's circled within the larger circle, that guy right there is a scalar multiple of A. And the reason why that's reasonable is if you look at a picture like this, it's pretty clear that whatever you think of the projection being, it's a multiple. Oops, I think I'm not sharing the screen. Sorry. It's pretty reasonable to think that whatever you think of P being, P is a multiple, a scalar multiple of A. And so what scalar multiple should it be of A? It turns out that it's this scalar multiple of A. So that's the scalar. So the numerator and denominator are just the dot products that we defined a couple days ago. So the numerator is the dot product of A with B, and the denominator is just the dot product of A with itself. So not only can we sort of conceptually work out what P should be in terms of the two vectors, we can work out with the formula what it is. So in general, P, so I'll write it down here again, just relative to that picture. P is the dot product of A with B divided by the dot product of A with itself. And what you see, just as a reminder, is a number. So we're sort of in a situation where we not only we really know we know how to project a vector onto a one-dimensional subspace of some larger vector space. That's how you do it. And so if people were left alone for days just to think about how you would handle the multi-dimensional case, the formula that most people would after struggling with it for a while, the formula that most people would come up with would basically be one in which the projection of P or the projection of B onto the subspace was just the sum of the individual projections, as though you're just writing down the coordinates of P. The coordinates of P could be worked out easily if you just think about how the individual or how B projects down onto the individual one-dimensional subspaces. So that the formula that people would really, I firmly believe this, but it might take a few days, the formula that people would really come up with would almost certainly, I think I wrote it down somewhere, would almost certainly look like this. It would be like, well, okay, look, I know how to project B down onto one-dimensional subspaces. And if I do that, I get a bunch of one-dimensional projections. Why isn't the projection for B just the sum of all of those projections within the subspace? And the reason why people would do that is if they actually, if you sat down and you played with a lot of examples, the reason why I think people would come up with that is that if you sat down and you played around with a lot of examples, if you just sat down and you thought about, well, what's likely to happen, the examples that people would come up with would probably all look like this. And the reason why the examples would look like this is because that's a natural choice of a basis within R4. So that particular basis, 1, 0, so the one that you see there spans everything in R4 except for one dimension. And if you have a vector like the one that you see here, like a B, it's easy enough to write down what the projection is. It is what you think it is. So the projection down onto the subspace spanned by those three vectors, it's natural to think that you would just get rid of the last coordinate. That if you have 2, 1, 3, 2, that's in some R4, you just drop it down to the subspace by eliminating the last coordinate. That's what most people would think the projection is. And in fact, in this case, it is that. When you actually write down the individual projections onto the one-dimensional subspaces, the first one you get, the projection down onto 1, 0, 0, 0, is 2, 0, 0, 0. Not surprising. The projection onto 0, 1, 0, 0 is 0, 1, 0, 0 for B. The projection down onto 0, 0, 1, 0 is just 0, 0, 3, 0. So the projections down onto the individual one-dimensional subspaces are exactly as you would expect. When you talk about projections in the context of coordinate geometry, this is exactly what people are going to think. They're going to think, look, I'm dealing with the basis that is standard. And because of that, my formula really should be just the sum of the individual projections. That's it. That's what they're going to write down, I think. That's, if you had a few weeks to think about it. And that's morally right. The truth is that's a really good idea. That's something that people would probably gravitate to naturally. It's a good idea. But it's wrong. But it's productively wrong. And why is it productively wrong? When you look at the normal equations, why are they so complicated if this is all that it is? In general, we guess, so I guess is what I'm saying, we guess that, I'll write it down in words, that the projection P is the sum of the individual projections Pi onto the one-dimensional subspaces spanned by the vectors AI. It turns out this is wrong. In general. But it is productively wrong. And so it's wrong in general because of the the normal equations. When you actually derive how to do this from first principles, you actually get something else. But it turns out you don't get something that far from what we're talking about right here. So the question about how you project, it really needs to be converted into a question, into another question. Under what circumstances is it true that the projection P is just, so into subspace of Rm, really what I think it should be. The sum of the projections. It is not in general the sum of the projections, but it is under certain circumstances. So The question about least squares is much more interesting when it's phrased in the second way rather than the first. So if you're talking about just least squares approximation, it's painful to read, but you can work out why, and you can work out why the normal equations are plausible. And it's got a lot to do with this notion of having a vector and you project it onto its shadow in some larger subspace and you write down what the matrix form of this is supposed to be. And you think about the fact that if you're dealing with a vector here, well, anyway, I mean, there's an argument. Even worse than that, the actual way that you show this is going to use techniques of calculus, which involve solving a bunch of linear equations coming from partial derivatives that are associated to the error term. Now, I don't, those ways are, it's useful to go through, some examples of those at some point just to convince yourself that the methods are reasonable. But it's not that interesting a question once you understand what the answer is supposed to be. The question that I think is of much more interest is something like this. My intuition tells me that the projection of a vector into a subspace ought to be different than what the normal equations predict. I'm confident, but yet I'm confident that the normal equations are correct. So what accounts for the gap between my intuition about the problem and what actually happens? And can I arrange a situation, or can I at least ask the question about what circumstances exist in which my intuition is actually correct? That's kind of where we're going next. So does that make sense? When you're thinking about vector projection, most people are going to think that if you have a vector like in R4, that the projection of that vector, if it's not in the span of some sort of subspace, is just going to be a vector in that subspace lacking a coordinate. So the standard basis, if you use that for R4, if you just take the first three vectors in the standard basis, you have some vectors not in the span of that, you would think that the projection of the vector that's not in the span is a vector that you would get by just removing the last coordinate or putting it to 0. There's your projection. It's actually true in that case. Your intuition is exactly what the normal equations would also give you, and that's interesting. The problem is, what is the discrepancy between people's natural view of the problem, their intuition about the problem, versus what the normal equations predict? And that's kind of where we're going next. So does the discussion make sense to you? We believe one thing. If you just sit down and think about how projections ought to work from an intuitive standpoint, we get one answer. If you look at the normal equations, you get an answer which is sometimes not the answer that you want. And so there's a gap between the intuition about the problem, which is totally reasonable, and what the normal equations would prevent. And what's that gap coming from? It turns out that gap comes from a certain property that vectors have that are spanning some subspace. So we'll get into that in just a second, but that's the discussion, I think. That's the way that you should sort of view, the discussion that's about to follow. It's not, the least squares problem is uninteresting if you don't think about it this way. If you view least squares, least squares is, the method and how you come up with the normal equations is like holy writ, right? Like it's there, but for that reason, it's not terribly interesting unless you really want to go through and think about how you derive the normal equations that carefully. But the interesting question is this: most people aren't going to get an answer which looks like the normal equations. They're going to get something else. And the reason why I think they're going to get something else, the reason I would speculate as to why they're going to get something else, is because their conception of basis is mostly that a basis has a certain property that all bases don't necessarily have. And we'll try to identify what that property is next. So, when thinking about that property, I'm going to bring up a set of slides, and we'll try to identify that property, talk a little bit about it. I think it's right here. No. Okay, hang on just 1 second. I need to import a document before I show it to you. Hopefully I didn't erase it. There it is. Okay. So the gap between people's intuition about projection and what actually happens, that gap is bridged by this concept right here. So it's the concept of an orthogonal matrix. That's what bridges the gap. So in the previous examples are the ones that we're sort of vaguely hinting at in this long discussion. The columns of the matrix A in the first example are not orthonormal, but the columns in the second example are. So that's what bridges the gap. I guess what I mean is that I did one example on another set of slides, probably not that critical to do it right now. But all this first point means is that if you take a look at 101 or 101 and 001, that type of basis for a two-dimensional subspace for R3 is not the same as a basis that looks like this. And if you're trying to project onto this two-dimensional subspace, the answer you get is what you think. If you try to project onto this, the natural answer that the projection is the sum of the projections, that formula no longer works. So when we're thinking about orthonormal basis, we're thinking about guys which tend to look like that and not guys which tend to look like that. In general, the orthonormal basis for a two-dimensional subspace of R3, they don't just look like the thing that's boxed on the right. There can have a more expansive view. Let's talk about what that is. So a set of vectors is orthonormal provided that their dot product is 0 mutually if I is not equal to j, and their dot product is equal to 1 if it is. If the columns of a matrix A are orthonormal, then R of A is spanned by some linearly independent unit vectors. So basically, if you have a set of n vectors, and it happens to be that those vectors are orthonormal, if you arrange those vectors in a matrix A where they're the columns of matrix A, then those vectors that are in the columns of A are linearly independent. They form a spanning set for RA. What's sort of amazing about a matrix with orthonormal columns is that if you take the product of A, if you take A transpose times A, you get an identity matrix. And that's sort of the key, and we'll get back to the normal equations in just a second and try to explain why the intuition works right when the vectors are orthonormal, but it's basically that property. So how do we actually see that? If you have an orthonormal matrix, if you have a set of orthonormal vectors, you take the transpose of the set of orthonormal vectors, you multiply by A, you get 1. One way of seeing that is that if A is an m by n matrix, if it has orthonormal columns, then the transpose of A, its rows are basically the columns of A. Over here on the right, you see the vector A, you see the matrix A with the columns being the vectors A. If you take the dot product, the ij position is equal to the dot product of AI with aj. So basically what we're saying is if you want to figure out what's in position ij in this matrix, just take row I and multiply it by column j. So basically in the 2, 2 position, you take A2 transpose times A2. But if the vectors AN are orthonormal, then A2 transpose times A2 is 1. But if you try to figure out what's in the 2, 1 position, then A2 times A1 is equal to 0 by definition. So the resulting matrix has 1s along the diagonal and 0s everywhere else. So orthonormal is nice. It gives you a way, it gives you kind of a left inverse to a matrix for one thing when the matrices are square. So the product of a transpose of an orthonormal, of a matrix that's orthogonal, that's what we're going to come to call this, a matrix which has orthonormal columns, A transpose times A is the identity matrix, and it has to do with the definition of orthonormality. So it's the classic example with the standard basis. It's pretty easy to check this property because it's equal to its own transpose, so I won't do that. But I might give you an example at some other point in time to check this. Even more interesting, the projection map in the previous set of slides has an exceedingly simple structure. So I want to talk about that for just a second, and talk about what that structure actually is. So the projection map that you're talking about comes from the normal equation. So the projection vector P of a vector B looks like this. Yes, it's a question.
I'm trying to just like kind of understand a bit more what orthonormal actually means.
Yeah.
Like I see the definition, and it's saying the dot product of two vectors if it's equals to 0. I'm assuming it's orthonormal, but like, what is it?
What is the practical meaning of it?
Yeah.
Yeah. So a set of vectors is orthonormal if each vector v sub I is at right angles with every other vector. And each vector sub I is 1 unit long. So that's what it means.
So what's the difference between just saying that like it's perpendicular to the other vectors? Is this talking about like a projection, or is this?
We're going to talk about that in a minute, but there is no difference. Each vector is perpendicular to every other vector in the set. That's what it means.
So
yeah.
Orthonormal is just describing, like it's saying that like v sub I is like relationship with all the vectors, as opposed to just saying like v sub I is like, as opposed to saying like if v sub I was perpendicular to like a vector, that's just indicating to one specific vector.
Yeah, so if you, I guess you could take it to mean that if you have a vector in a set, and if it's an orthonormal set, then if you take an element at random and then think about its spatial relationship to the other elements in the set, it's perpendicular to everything else in the set.
Okay.
It's not perpendicular to itself, right? That wouldn't make sense. But it turns out that the condition that VI transpose VI is 1 is the same thing as saying that the vector is 1 unit long.
Okay, that makes sense. Thank you.
Yeah. So there are lots of examples of orthonormal sets of vectors. You know, the standard basis that you normally write down, or subsets of it, have that property, but they're not the only thing that has that property. There are a lot of examples of orthonormal bases, and the reason why, from the point of view of projection, from the point of view of the intuition about how projection ought to work, the reason why they're important, from the point of view of, didn't mean to do that. The reason why they're important from the point of view of projection is actually this property right here. So this is important. And it's important because the normal equations involve this weird combination of matrix, this big product of matrices, which is supposed to be doing the projecting. If A has orthonormal columns, then A transpose A is the identity matrix, and the projection is just A transpose B. Now, it turns out, though maybe it's not so obvious, that the right-hand side is just the sum of the one-dimensional projections. So the condition, so it again, I mean, so is there another question?
Sorry, no, I just didn't.
Yeah, sorry. So, I mean, just to recap, if you're on a desert island and you're thinking about how to project a vector into a subspace, like if that's the problem you're trying to solve, and you've taken some linear algebra and you only have that to think about for weeks, the way that you're probably going to, the method that you're probably going to arrive at, after some thinking, is that if you want to project a vector and you have a pretty good handle on how to project that vector onto one-dimensional subspaces of this larger subspace you're talking about, you're liable to, first of all, think that the individual one-dimensional projections are in some way related to the projection of B onto the whole space. And of course, you're not wrong about that. But the next guess that people are going to make that winds up being wrong but good is that the projection of B onto a subspace is just a linear. I mean, it's not just a linear combination of the one-dimensional projections. Of course, it is that in the normal equations, but it's that it's a particular linear combination of the projections. It's just the sum of them. And the intuition that people build up, to get to that result is based on having a very particular orthonormal basis for Rn. It's the standard basis. And within Rn, if you have a subspace which is spanned by elements coming from the standard basis, that's absolutely the correct answer. The projection of P, the projection of B onto some subspace spanned by some subset of the standard basis, all you're really doing is you're adding up the individual projections onto the coordinate axes, and that's the projection. So that's right if the basis you're doing is that particular basis. But if your basis is weird, it's not. And things don't work in the way that you would expect. So I've been thinking for several days about a problem that would actually show this, and I think I'm going to have to think about two dimensions rather than I'm going to have to think about two-dimensional space with some weird coordinate axes just to try to work it out. But it's an exercise I'll probably put on a later written assignment, probably not the one for next week. But it's a good exercise, I think. To think about why under what circumstances does your intuition about the problem break down? And that's why, at least to me, projection is interesting. It's not because you get least squares approximation. You can do that with a computer. It's because it leads to a question about a gap between something that you think ought to be right and something that is right, and how those things are different. That's always interesting. And the thing about it, because they usually allow you to come up or refine what you're thinking a little bit, to come up with a condition that we need to be right, and that condition looks like this. So if the set of vectors AI that you're dealing with is orthonormal, it turns out that your intuition about the projection is right. The projection onto a subspace spanned by orthonormal vectors is indeed the sum of the individual projections of B onto the one-dimensional subspaces. It's an exercise of sorts to kind of work out why that is. I don't know that I want to write that down because it's probably going to wind up being tedious for people. But if you look at the right-hand side, A transpose on B winds up just being, P sub 1, P sub 2, P sub 3, all added together. It's not too bad to work that out, but it's sort of, when you have at least an orthonormal base, when you have orthonormal columns, it is anyway, not in general. So, when you're thinking about projections, projecting onto a subspace of Rn that is spanned by orthonormal vectors is extremely easy, because all you have to understand in that case is how that individual vector B projects onto the individual one-dimensional subspaces. Once you understand that, to get the total projection, just add up the original, the one-dimensional projections, and that's your guy. The problem with some more general situation where you don't have an orthonormal basis, in essence, what makes your intuition wrong is the presence of a non-identity matrix right here. The fact that A transpose A is not necessarily the identity matrix in the general case, that's actually what confounds the intuition. So A transpose A inverse basically is an adjustment term for the weights associated to the projection of B onto the subspace. It combines the weights that you would normally expect to see if you think that the projection is the sum of the projections in ways that are weird. And so basically that particular vector, that's the issue, and that occurs because if you have coordinate axes which aren't which aren't at right angles, which aren't perpendicular, you wind up, anyway, I mean, the basic issue, I guess, what I want to say is the basic issue is that if you're thinking about vectors now as coordinate axes, then not having them at right angles screws up the process a bit to the extent that you need that extra correction term in the normal equations to get what your intuition tells you ought to be true. And so to make your intuition right, you want to be dealing with an orthonormal basis. What most people are going to say at this point is, well, okay, my basis that I start with is whatever it is, right? If it's not orthonormal, then I guess you're just out of luck. But it turns out that that's only partially true. You're not totally out of luck. So before I move on, do you see what I'm trying to say with this? When you think about vector projection, just visually, people are really going to be working with the standard basis when they think about this problem. And in the standard basis, in order to understand how a vector projects onto a subspace spanned by some subset of such a basis, you just have to think about how the individual coordinates work of the vector. You are essentially zeroing anything out that is not spanned by elements in the standard basis, and that's the projection. But that doesn't work in general. And so, you're trying to identify a situation where your intuition about how things will work would be right. It turns out that the condition that you need is that you want to think about vector subspaces of Rm, which are spanned by an orthonormal set of vectors rather than just any old basis. If it's true that the subspace of Rm is spanned by a set of orthonormal vectors, then all you really need to know is how your vector B projects onto the individual vectors within that basis. And if you know that, then you basically know how the projection works, because all you've got to do is add up the individual one-dimensional projections. It works like the standard basis in that case, is what I'm saying. So all an orthonormal basis is the generalization of the basis 1, 0, 0, 0, 1, 0, 0, 0, 1. Things work well when the basis is orthonormal relative to projections. You get a nice decomposition of a projection map, I guess is what I'm going to say, when it happens that the basis is orthonormal. It's not an unimportant fact. So before I move on, does anyone have any questions? What I just said is pretty hard. Takes a while to absorb, I think. So we have the definition of orthonormality, at least. To talk a little bit more about orthonormality, I want to probably just have, talk about things in less abstract terms. I'd like to have people do a couple of examples. So this particular matrix Q, this is just a 2x2 matrix. Theta is some number. What I want people to show when you say that Q is orthogonal, what I'd like people to show here is that the columns of Q are orthonormal. Shouldn't take too long to do it. Come back together and do it in just a few minutes. The columns of that Q are orthonormal. Right now about 1140. Remember that when you're talking about an orthogonal matrix, you're just talking about a matrix in which the columns are orthonormal. So you have to show that the column vectors have the orthonormal property. So try it, see what you get. We'll come back in about 3, maybe 5 minutes, about 11:45, do the problem together. If you get done with that, think about the problem that follows. Show that permutation matrices in general are orthonormal. That problem is probably too much of a mess to work on maybe right now. So maybe just take an example and show it's orthonormal or orthogonal. So maybe try those two. Take an example of a permutation matrix, show that it's an orthogonal matrix. Maybe try the first example. Probably can do that in maybe 5 or 6 minutes. So try that. We'll come back in 5 or 6 minutes to discuss further. All right, so back to the handout, back to the set of slides. If you have, in the first case, some people I think this is often called a rotations matrix, has a lot to do with the geometric significance of what this matrix does to vectors in R2. You want to be able to show, so for one, so you want to show that the columns of Q are form an orthonormal set, are orthonormal for short. And so, this involves just sort of checking some things. So one of the columns is cosine theta, sine theta. The other is minus sine theta, cosine theta. So you're trying to see that the columns are at right angles for any choice of theta you could possibly make. So, first of all, are they normal? Are they unit length? So if you have, let's call that, yeah, don't really need to give it a name, but yeah, I guess I do. So maybe that's V1, maybe that's V2. Need to give stuff names because I have to think about what I'm talking about. If you take V1, if you try to measure how big it is by taking its dot product with itself, you wind up looking at something like this, but that's the same as cosine theta, sine theta times cosine theta, sine theta. And if you think about it for a minute, it's the same as cosine squared theta plus sine squared theta, just 1. So that is a normal vector. It is a unit vector, right? It has size 1. For V2, we can check the same thing. So we look at V2 transpose V2, the dot product. And so you get minus sine of theta cosine theta minus sine theta cosine theta. Yeah, go ahead. I'm sorry?
Sorry, you said this is finding the length?
Yes, that's right. Yes, it's finding the square of the length, but that's close enough. Yeah, it's size. Yeah. And so if you get 1 out of this, you're saying that the vector is 1 unit long, I guess, because the square root of 1, the positive square root is 1. So you take the dot product here, minus sine times minus sine gives you, of course, a sine squared. Cosine and cosine product gives you cosine squared, and that's also 1. So at least the vectors have the right length. Now you want to show that they're at right angles, and so there's an additional calculation that you actually have to do. You check to see that V1 transpose times V2, the dot product sets 0. You're hoping that's true. So the first vector is cosine transpose cosine theta sine theta times minus sine theta cosine theta. So what do you get? From the first guy, you get a minus sine theta cosine theta plus sine theta cosine theta. So of course that's 0. So of course, if you do the calculation the other way, I guess you could probably check that V2 is orthogonal to V1. But if one thing is at right angles to something, then the other thing will be at right angles to the other thing. You just have, in terms of vectors, you just have to think about the transpose to see that. So we see that the set of vectors is actually the is orthonormal, right? It's more than just orthogonal. It's more than just being at right angles. One question that one can ask after seeing such a problem is, okay, that's a 2x2 matrix, and any 2x2 matrix which looks like that is an orthogonal matrix. It has orthonormal columns. If you think about the set of all 2x2 matrices, you could ask, do they all look like that? So if you take a given 2x2 matrix that you happen to know is orthogonal, does it look like that matrix we just saw for some choice of theta? Turns out the answer to that is no. There are examples of orthogonal matrices which don't exist as rotations. One particular example is a permutation matrix, which is sort of related to the next question. So for the next question, you take any 3x3 permutation matrix, you show that it's orthogonal. I think I probably will hold off on doing that right now. Maybe you've already done it. Just write one down, take its transpose, see that the product of the see that the products of the columns work out in a certain way. So it's, yeah, so, well, I mean, or just take any one of them and just check the products to see what you get. So I won't say too much about that. Might leave that as an exercise for some later written assignment. So at this point, to sort of sum up, it turns out, that's an important property. We'll talk about that next time, maybe. Orthogonal matrix is important for us, basically because of the property that you see right here. It's sort of a matrix which doesn't do a whole lot to vector to the geometric relationship between vectors x and y. So it's a transformation. I mean, one way of thinking about it is sort of it's a transformation of Rn to itself. That sort of doesn't really change the geometric orientation of the vectors. It winds up being important. I'd probably want to talk a little bit more in detail about what's next to that arrow next time, rather than just sort of doing the calculation and moving on. So I think right now probably it's decent time to stop. It's about 11:53. I'm not today. I had intended, I think, to get to things like Gram-Schmidt process and QR factorization, but that'll wait until next week. So as a preview, the idea behind Gram-Schmidt is this. When you are dealing with an orthonormal basis for some subspace of Rm, talking about that subspace becomes extremely easy. Among other things, among other things, if you're trying to project a vector down onto it, for example, projections are really easy to understand as being the sum of projections onto one-dimensional subspaces. That is actually an important fact. And so the geometric, understanding the geometric structure when you have of a subspace, when you have such a basis, is easy because of the nature of the basis. Much harder if you don't. So, if you're dealing with the basis like for a null space or for a column space or something like this, if you're dealing with vector projection, you might think that you're out of luck if you're just stuck with some random basis that just comes out of some set of equations. And in a sense, you're right. It's hard to deal with that. It turns out that there is a way of taking a basis for a subspace of Rm, any old basis. It's possible to convert it into an orthonormal basis through something called Gram-Schmidt process. So we'll describe how that process works. Gram-Schmidt process is an example of something. It's a lot like least squares, where it's better to understand or have some idea about how the process works than it is actually to be able to conduct the process by hand. And the reason is that in any practical application of the Gram-Schmidt process or anything like it, you're not going to be calculating an orthonormal basis on paper. You're generally dealing with high-dimensional vector spaces, and the computer can equipped with a linear algebra package can do this. You won't be doing it. You really only do a couple of examples to understand how the process is supposed to work and to convince yourself that it makes sense. So we'll describe the process, maybe do a calculation or two, but to be honest, the calculation is much less important to me than understanding what the process is doing. It's also important to me to understand for you to understand why an orthonormal basis is better for a lot of applications than just a regular rule basis. But we'll talk a little bit more about that, I think, next week as well. So we're going to stick around and talk about orthonormal bases and orthogonal matrices, I think, for a little bit more time, rather than just moving through it. So we'll end right here. A couple of additional comments. I'm going to put a written assignment 3 up. It's going to actually be a pretty minimalist assignment. We're about halfway through the course. I think people are probably beginning to be tired. Use this weekend to catch up on some things. So I'll give you a written assignment. It's going to be some calculations that you could do, turn in on Monday, maybe 3 problems. And maybe that's about it. So be on the lookout for that maybe later today. There'll be calculations maybe that, you can verify that something is an orthogonal matrix, or, you can calculate the projections using a formula. Maybe I'll probably put question 6 from written assignment 2 on it. Maybe those are the 3 questions. You can have a chance to go back and think about question 6. So it's, use this weekend, catch up on some rest, finish the written assignment, catch up on other things that you might be doing. And I guess that's it. So I guess class over. I'll have an office hour at 1. If I see you there, that's great. If not, see you next week.